Hello everyone. In this video we are going to see the self-attention mechanism. We will understand it step by step with simple examples, and we will keep it simple. We will not go into much details, complex details, right? And at the end we will also understand the intuition behind how it is able to generate the context of the given sentence. So yeah, let's get started. So, what is self attention? So, in mathematical terms, the self attention is simply a formula, simply an operation that is performed on given arrays or given matrices, right? And we perform some operations on the given matrices, and we get a new matrix that is referred to as this term called as attention, right? So that is what basically it is. So but in our domain, in natural language processing domain, if we want to use this concept of self attention, so we can refer it as a way to capture the relationship between the words, among the words in the given sentence, right? It will be able to capture the context of the given sentence. It will be able to capture the relationship between two given words. That is how we will be using this concept of self attention here. So let's understand it step by step. So we will take example of the following sentence: I like cricket more than hockey. So we'll use this sentence and we will see how this context is captured. First thing we do is to split the original sentence into smaller parts. Now in this case, suppose we are splitting this original sentence into words. Okay, so there will be 6 words, right? And these smaller parts are known as tokens, right? So here we have 6 tokens, right? Each token will be represented by this letter T, suppose. So we have these T1, T2, T3, T4, T5 and T6, 6 tokens. Each of the token will be converted to numbers. So basically, as we all know, the computers do not understand the letters or the words as such. They only understand numbers. So our job next is to convert these words into a list of numbers so that the computers would be able to understand it. Now these list of numbers are they are called as word embeddings, and these word embeddings are nothing but they are just a list of numbers. Okay, so suppose we have this word I here, and this I word will be represented by a list of some numbers. Suppose there will be some sort of numbers, right? Whatever they are. So suppose there are such 512 such numbers, okay, which are representing this word I. So likewise, each and every word will be represented with the list of numbers. Now how is this list generated? This list is generated with the help of a neural network. Neural network is relatively pretty simple, by the way, but we're not going to go into much of the details. We'll just see what it is in brief. So this is what the word embeddings are, and the special thing about the word embeddings is that the similar kind of words will get assigned similar kind of numbers. For example, I, we, you, all these are similar kind of numbers, right? So they will have similar word embeddings associated with them. Likewise, maybe this is 6, maybe something like 10, 9, whatever that is. Okay, so the similar words get associated with similar numbers, and different words will have different sort of numbers, right? So this I will have a totally different list of numbers compared to the word mango. Okay, and this mango word will have similar set of numbers with apple or all the fruits. Okay, so this is how the word embeddings work. Okay, so this is what they are in short. So in short, they are just a list of numbers. Now a list of numbers is also called as a vector more formally. Okay, so they are also known as vectors. So each of the token will be represented as a vector, and let us denote the vector by the letter V. Okay, so each of this T1 will become now V. Okay, so now each of this token or the word is represented by a list of numbers. Now this list, each of the list contains 512 numbers. Okay, they contain 512 numbers. Now this let's keep it simple. Okay, so it has 512 numbers, each of the VI. Alright, so now we have 6 lists. So what we will do, we will stack them together. Okay, so we have 6 vectors representing 6 words. So we will uh, uh, represent all these 6 vectors with a single matrix. Okay, or a single array or single multi-dimensional array, that's what you can call. So we have these 6 v1, these 6 vectors, right? And now what you can do, you can represent that using a multi-dimensional array. So this is how the multi-dimensional array will look like, and it will have dimension of 6 cross 512. Now it means that we have 6 rows, and each row has 512 numbers, just like this, right? And we will denote it by this variable or this letter Q. Okay, so Q is now our input matrix, which contains all the information about our input sentence, right? Now the next step involves finding out the similarity among the words. Okay, so in the next step, what we will do, we will perform an operation called as dot product among the vectors, and we will find out how the similarity is found out. Okay, so we calculate the dot product in this next step. Okay, so how is this dot product calculated? So what you do, suppose you have these given 2 words, right? Suppose you have this I and you have another word as V. Okay, so you have these given 2 words and they are represented like this, whatever 3 4 5, whatever that is. So how well, now what we do is we take these individual components, okay, the corresponding components, and we multiply them together, and then we sum it all. We take the sum of all these multiplied results. So for example, I'll tell you. So suppose here the dot product, so maybe dot product will be something like this. So this first one into first component, and then you plus second component into the second component, plus third component into third one, and so on. Okay, so this is how you calculate the dot product, and that this operation will give you some number, right? So you will get a numerical value, right? And now this numerical value will be representing the similarity between the 2 words. So for example, we have these 2 words here, I and V. So we will have high value, high numerical, high positive value for these 2 words, because they are similar, right? And then if we have completely different 2 words which are not related, then you will have maybe negative number, and then that will be higher in magnitude as well. So this is how this similarity is represented with the help of dot product, right? So our next job is to perform this dot product with each pair of the words of the words in our sentence, right? So from this original sentence, we will perform dot product for each pair, something like this, and then again I with cricket, and then again with more, and with each word, right? Then again with similarity between like and cricket, and then these two words, and then again this, cricket and more. So each pair, we'll consider each pair, and then we'll compute the similarity. We'll compute how similar the given two words are. Okay. So the other thing about this dot product is its notation. So I'll just quickly tell you. So suppose we have this, we will represent this as v1, and suppose this is represented as v2, then the dot product presented like this. Okay, so you take this v1, you put this dot here, and then you have this v2, and then this is some t. Now this t means transpose. So what this basically means is that you have this v1 vector like this. Okay, and then what you do, you take this v2 vector and you invert its dimensions like this, and then you then it will basically represent that you take the first component and then second component, you multiply all them and then add together, and you'll get some number. So basically that just means the same operation. Okay, so it need not be confused. We will calculate the dot product of v1 with respect to all the other vectors. Similarly, you will take v2 and you will calculate the dot product of v2 with respect to all the other vectors, right? Similarly for v3, v4, v5 and v6, right? So that will basically give us the similarity scores. We will call it similarity score among all the given words. So this has a way of representation. Okay, so we represented this matrix with q, right? So we have this q matrix, and just as I've told you, this q transpose, okay, the q transpose, what you will do, you'll take the rows and you'll convert them into columns, and that is the transpose operation. That's it. So this transpose matrix will look like this. Okay, so this is how it will look like. This v1 is now this column, v2 is this column, v3 is this, all this kind of thing, and each of these column contain these corresponding 512 numbers associated with the word embeddings. So this is how this transpose looks like, and you will see why we have done this. Now what you can do, you can take this v1 and you can multiply it with this matrix. That will give us this transpose, just like what we have done here. Right, so this transpose. Okay, you can see that you had this matrix like this, and then you had this matrix like this, and then we were able to calculate the dot product, or that is how we represent the dot product. So now you will take v1 and you will multiply with all of this qt, which will now give us v1 transpose, v1 v2 transpose, v1 v3 transpose, all these. Then again you will take this matrix and do the same. You will take this matrix and do the same. So we will be able to perform exactly this operation, right? So this is how we will represent it. Q, which was that original matrix, dot q transpose, right? Something like this. So you have this q, so you say this is q, and this is called as q transpose. And now you have all these vectors v1, and this is basically actually this is v1 transpose, and then you have the similarity scores. So you can see that this will give us, so this is the general rule of matrix multiplication, and this is 512 cross 6. So this matrix multiplication basically gives you a 6 by 6 matrix, but we need not go into that details. So you can see that clearly you have clearly you can see that you have this v1. This will be there will be 6 dot products, right? with each of these vectors. Okay, so we will have 6 numerical values, right? So that is, so we will have 6 numerical values. So basically you have this 1, 2, 3, 4, 5 and 6. So we have these 6 numerical values, and they, the first one, they are related with v1. Similarly, it will be related to v2, it will be related to v3, v4, v5 and v6. Okay, and then they, all of them will have 6 such values, right? So this is v1, this is v2. Okay, this is not the right way to represent it. Basically what this matrix is denoting is this. So you see this. So now you can see that this similarity scores matrix represents the similarity scores of each word with the other word. Okay, so this was the dot operation we performed, right? We performed the dot operation of v1 with every other vector, right? So this is what we got. Okay, this is the same matrix 6 by 6. So basically what that operation meant, that you are performing the similarity, you're checking the similarity of this word I, because I is represented as v1, right? And that is what we did. That is what we did. We took v1 and then we perform the dot product with each of the other word. So this becomes we performed the dot product with I like cricket, more than hockey, all of these 6 words, and we got some scores. So what these scores now represent is the similarity, how the given how similar the given two words are. Maybe I and I will have obviously a high sort of similarity. Maybe this is 100. Okay, so these are just random numbers. Okay, and maybe I and like will have another kind of similarity, 5. Maybe cricket will have, all these kind of words will have high, maybe cricket and hockey will have high similarity, like maybe 50, who knows. So these scores are now representing the similarity between these two words. So you can see, suppose if you want to calculate the similarity between cricket and more, so you go here and you have this number which is representing the similarity, right? So this is why we perform the dot product, and this is why this dot product is really helpful to find out the similarity. So now obviously these numbers are very random and large. They're not up to scale. So what we will do something called as normalization. Okay, we will also bring them down by dividing some number. So here that number was 512. So you can see we had this formula. This is what it is. Q and K represent the same matrix here. Q is our input matrix and this K is also the Q in this case, and V is also the Q. So basically Q, K and V are representing the same matrix, and by doing that we are able to calculate this attention. So this is root D. So this D was the number 512. So the number of components, or the number of numbers in the or simply the size of the vector representing this word embeddings, that is our D. And then we will divide it with that number, which is 512, and then we normalize it. Normalize it means we will convert these values such that they will all sum up to 1. Okay, so for example something like this. Okay, so you can see likewise you will have all these this will be done for all of the rows. So for each row you will see that they all add up to 1. So this is 0.5, 0.5, 0.2, all these this is 0.05. so these all numbers will add up to 1. So now these are not drawn to the scale, or they are just random numbers, but just understand that this is what normalization is. So now we have a final matrix which looks something like this. Okay, and we will call this final matrix as similarity scores matrix because they contain the similarity scores, right? So now you can see that we have this similarity scores matrix. Okay, so this was an important part and this is done. So we have calculated the similarity scores of all the words, right? All the related words. So what's next now? So now these scores can be imagined as the weights given to each other word with respect to another word. Now what I mean by that is that suppose you have this word I. Now with respect to this word I, what weights are given to the other words? Obviously I with I will have the highest weight because it is the most similar word. And then maybe suppose, now these are just random numbers, okay, I have not drawn it actually, by performing some calculation. These are just random numbers. So suppose I and like are, and I and cricket are these two most similar words, okay, compared to these three. So they will have 0.2 and 0.2 number, and then more is more similar. So suppose you have this 0.1 value given to it, and these are the least similar words, so therefore they will have 0.05 and 0.05 associated with them. So similarly you will have all these matrix, right? You will have all these weights as this. Understand this significance of this matrix or the meaning of this matrix. So these two words have 0.2 as the value, hence you can say that they are 20% related, okay. uh, I and word more is maybe 10% related. I and than, these two words are 5% related, and similar for randomly, I'm telling it randomly. So that is what it means. So you can think of, you can imagine if these scores as the percentage of their similarity, right? Suppose in our sentence we had the words mango, and then you had this word fruit, and then you had this word animal. So we may have got in our similarity scores matrix that mango and fruit would have been 50% similar, and whereas mango and animal would have been just 1% similar. So something like this, that is what this matrix is representing. So up to this point we have covered these parts, okay. We had this input matrix q, we multiplied it with this q transpose. As I have mentioned, qk we had the same, so we multiplied with q transpose here, you can see, okay. And then we got these similarity scores, right? Then what we did, we divided as they were of random scale. Some will have maybe 100, some will have maybe minus 100, maybe something like that. So what we did, we scaled them down, okay. And we normalized, and then we again added softmax here basically. So we normalize them, so we scale them down, okay. And then we added softmax basically means that we converted them such that they will all sum up to 1. So that is the operations we performed so far. So why we perform the softmax, why we made them to add up to 1, you could see that here we can deal now with percentages. These all now represent the similarities in percentages. So that's what we did, that's why we did it. Okay, so we have this much part, okay. Up to this much we have covered so far. Now comes the most important and crucial step of multiplying it with the v means the same matrix as I've told you. So what is the next step? The next step is to take this similarity scores matrix and multiply it with the input matrix, okay. So in short it is something like this. So So this is your this is our similarity scores matrix, and this is our input matrix Q. So suppose I'm representing each of these similarity scores by something like this: S1, S2, so basically S1 represents the similarity scores of the first word with all the others, like this. Similarity scores of I with all the others. Similarly, all the S will represent these scores. So this is your matrix, and this is our input matrix. So where this is our V1. This was the word embedding of the word I, right? V2 and all the other. Okay, so how is this matrix multiplication performed? So basically this matrix multiplication will result into another matrix. So how is this first row obtained? Okay, so this is the new matrix, and these are the 6 rows of the resultant new matrix. So how is this first row obtained? So basically what happens, or the rules, according to the rules of matrix multiplication, this this element, this first element, okay, so just let us call it first element E1. So this E1 will be obtained by multiplying this S1 whole S1 vector with this first column. Okay, so all this this first column, and then the resultant values will be added. So basically we are taking the dot product. So you're taking the dot product of S1 with this first column, and then this E1, we will get this E1, and then this E2, the second element, will be obtained by multiplying this first row with the second column. Similarly, you will have 512 columns, right? And they will all be multiplied, or the dot product operation will be performed with respect to this S1. So basically this first row and this first column, then again first row, second column, then again. So similarly this first row, first column will give us this, then this first row, second column S1, and with this second column will give us this value. So similarly you will get all these values, right? So you can view this multiplication as like following. Okay, so as I've told you, this first row is obtained by the multiplication of this first row here of this similarity scores matrix with this input matrix, right? So you can view it like this. Okay, you can view it in this way, that you have this this S1 as this is your S1. So more formally it should be written as S transpose, but let it be S1. This is your S1, and this is your input matrix. This is your Q of 6 cross 512. Okay, so there are these 6 vectors, and here there are 6 scores. Okay, you can see very it matches very beautifully that you had this scores, right? You have this scores of word I with respect to all the others. So these are the scores of word I with respect to all the others, and these are all the other words. Okay, these are the 6 given words, and these are their similarity scores with respect to the first word, which is the word I, and that is what we are multiplying. So what was that initially? So maybe here it was 0.4, 0.2, something like this. So from this matrix you can take this here. So this was 0.4. See that as the word I and cricket were 20% related, this 0.2, this cricket vector gets 0.2 times multiplied. So basically we are, what we can say is that we are taking 20% of the word cricket. Okay, so basically we are multiplying all these weights with these vectors, and then we are taking the sum. Okay, and then that becomes our new vector. Suppose let us call it v1 dash. Okay, so this new vector v1 dash is obtained by multiplying these individual scores with their embeddings and then taking the sum. So basically this v1 dash contains percentages of these words. So you can say it contains 40% of its original word, which is v1, so it contains 40% I. Then it contains 20% of word, the second word, which was like, and so on. Okay, so that is what it means. Now to understand it even better, uh, take we will look at the example which we had taken. Now when we generally we as humans, when we generally look at this word cricket, this word alone will mean two different things, right? It will it represents a type of sports, right? And it also represents type of insects, you know, those who make noises at night. So we we get two different meanings from the same word as cricket, and the same happens with the computers when they associate word embeddings with the word cricket. They have inside them the numbers somehow contain the information about the sport and about the insect as well, right? So far so good. But when we look at this sentence, I like cricket more than hockey, we get very clear that we are referring to the type of sports, right? And that is what we want the computers to do as well. And that is why we did all these things, you know, we calculated this self attention, and we performed all these calculations. So what basically happened now is that the problem was that even if we had this sentence, the word cricket contained the same number, right? It also contained information about insects, right? Even looking at the sentence, that's what we wanted to do. That's what we wanted to teach the computer, that we are referring to sports, right? And that is why we created new set of numbers, right? So basically these new set of numbers uh, contain the other words according to their similarity score. So for example, this word, the new word embedding for cricket will contain 40% of its original numbers, right? Here it is 0.4 times v1, right? And it will contain these other numbers as well in small amount, and mainly you can see that it contains, suppose that 0.3 times this word embedding of this hockey. So it will contain 30% of the numbers of the word, the numbers representing the term hockey, right? And as term hockey is closer to the word sports, these new numbers representing this word cricket will be closer, or they will look similar to the words or to the numbers representing the word sports. Okay, so that is how this new word embeddings which are representing this word cricket are closer in their representation to the word sports. And this happened because we did all these self attention calculations. We calculated similarity scores, and then we took these percentages, percentages of all the words according to their similarities. So that is how we were able to generate the context. We were able to tell the computer that this cricket word now is more similar to the word sports based upon all these calculations. So yeah, that's it. And that is how we generate the context. So basically this is a simple representation of everything. Actual implementation of this self attention mechanism is a bit complicated. It involves more than this. It involves query key and value matrices. Basically they are multiplied with the input matrix, and then self attention phenomena is captured. And basically these query key value matrices have trainable weights, means the weights that can be trained, and also it has multiple attention heads and all this. But this video was meant to be a simple meant to give a simple intuition of how basically this self attention is working. So yeah, that's all, and thank you.